In this video, we're going to talk about three topics. The first two are pretty quick. Chemical and physical change you covered in your first year course, so it's really just review. And then we're going to spend most of our time on reactions and especially net ionic equations. So we'll start with physical and chemical change. You might remember from your first year class that a physical change is when physical properties are altered, but the actual substance doesn't change what it is. Okay? So change in state is a really good example of that. Okay? You're changing how spread out the particles are, how much energy they have, but you're not changing what those particles actually are. So in a physical change, interparticle forces may be broken, but the bonds are not broken. Now I put broken for IPF in quotes because they're not actually broken. They're not bonds, they're attractions. So they're really just overcome. Okay, so those interparticle forces like hydrogen bonds, dipole, LDF, that stuff that you learned about in first year chem, those can be overcome in a physical change, but they're not actually broken. Chemical changes, something new is being formed. Okay, that is the telltale sign. So on the microscopic level, what's actually happening is bonds are being broken and then they're being formed. The bonds that make up our reactants are being broken, and then new bonds are being formed to make our products. So a nice example of this is water. So we have two versions of changing water here. The first one, the electrolysis of water, we'll talk more about this throughout the year, is when you use intense amount of heat in water to actually break up the hydrogen and oxygen. Okay, so you'll take our bonds here and you will break them apart. So you will end up with a new bond between two hydrogen atoms and then oxygen by itself. Now, obviously, we know that's not true, but that's the way this equation is written. So that's just what I'm going to write for now. Okay. The important thing here is that bonds are broken, new bonds are formed. In a physical change, which I know this is cut off, so I'm just going to rewrite it. That's not happening. It's H2O both times. The only difference is we're going from liquid to gas, so we're just spreading it out more. Okay, so that means some interparticle forces need to be overcome to break up, the different particles, but we're not actually breaking any bonds that hold the atoms together. So that's a physical change. Here are some guidelines for chemical change indicators. Now you'll notice for the first three I added spontaneous. You have to use your common sense here. You don't want to think, oh, there's a change in temperature, so automatically it's going to be a chemical change. Is there an easy explanation, like for example, you heating it up on a stove, that accounts for the change in temperature? If there's an explanation that you could have given before chemistry class, then it's probably not spontaneous, okay? But if you see a spontaneous change in temp, smell, or color, that might be a chemical change. Formation of a gas, which is bubbles, you'll see that a lot this year in the lab, that is not a change in state. So if we know that it's just boiling, that's different. And then formation of a solid, that is not a change in state. So you don't want to say, oh, I put the water in the freezer and it became ice. Still H2O, not a chemical change. Okay, so these are some guidelines to kind of get us talking about that, but these are not hard and fast rules. You have to still use your common sense. One thing that shows up a lot in AP is they give you a data table and they say, okay, before the reaction, it weighed this much. After the reaction, it weighed this much. Okay, and there'll be an increase in mass. That's formation of a solid. The reason people get tripped up by this is because they forget about air. So they think, oh, there's nothing for it to react with, so it can't be a reaction. So it will say something like, we heated this up, and then after we heated it up, the mass increased. So people will say physical because we just heated it up. We didn't react it with anything. Don't forget about air. Air has a lot of stuff in it. There's O2, there's N2, there's tons of stuff floating around in there, CO2, all kinds of stuff that something can react with. Okay? So if you see an increase in mass and you want to say physical change, take another look at it. Was it open to the air? Because it might be a chemical change if it was. Okay, obviously look at the whole picture and all the information you have, but don't forget about air. And honestly, that's pretty much it for chemical and physical change. So you'll have some practice questions in class and you'll take a look at them, but that's really all you kind of need to know notes-wise, and the rest is just going to be practice. So we're going to move on to net ionic equations. Okay, so net ionic equations basically are when we take out the stuff that doesn't react. Okay, so we take an equation, we take a chemical reaction, we start with a balanced chemical reaction, and you then cross out the stuff that doesn't react. Okay, you do not have to write states of matter. You quite frankly should not, because it gets you into trouble. Don't write more than you need to. And you're also going to start to notice that we're going to need to predict products and we're going to need to translate reactions. And I know we did that over the summer as well. So you're going to get so good at this because we're going to do it all year. One of the reasons I'm putting this unit at the beginning of the year is so that we then have a chance to practice it all year because it's so important. So keep that in mind. But for now, kind of take a look at it, see single, double, replacement, combustion, whatever, when you're reading the problem, and do your best to predict the products, okay? Keep in mind the naming rules. You are going to need to crisscross the charges, all of that stuff that you learned in first year chem. If you need practice with that, that's fine. You have the whole year, okay? So definitely get the practice that you need. So something that's probably new to a lot of you, if not all of you, is solubility rules. We're going to use these in our net ionic equations. Okay, this is the full set of solubility rules. I want you to have it. I want you to have it in your notebook, which is why I put it in the notes. I want you to be able to reference it. Okay, the reason for that is because if you need more practice with net ionic equations and you come to me for a set of just practice, you're probably going to need to reference these. Okay, so that's why it's there. For AP, you do not need to reference them. Okay, you only need to know these. Na plus, K plus, and NH4 plus is always soluble. So if you have an ionic compound, also known as a salt, you'll hear us use salt a lot, and it has Na, K, or NH4, we assume it's soluble. Also, if it has nitrate, we assume it's soluble. Okay? If it does not fit one of these rules, then we assume it's insoluble. Now, all of that said, there are also going to be some indicators in the problem that might indicate that it would be soluble even if it doesn't follow one of these rules. So this is the list of kind of ideas of what that might look like, but just, again, use your common sense when you're reading a problem. All right, I don't expect you to memorize this. I do not think it is worth your time to memorize this. You'll have it in your notes while we're practicing throughout the year. You can always go back to it and take a look at it so that you're familiar with it. But this is definitely not a memorization thing, okay? This slide is, this little box is. This you need to memorize, very quick and easy. You probably could do it right now. NaK, NH4, NO3. Those are the soluble compounds. So you'll also notice that there's some reference to acids in here. We're going to be using acids. We're not going to actually get to the unit of acids until unit 3, but I'm just going to throw them in there so you have exposure to them. And because you don't know what's strong and weak yet, I'm just going to tell you. Okay, so weak acids need to be written as a molecule. Strong acids can be ionized or dissociated. So for single replacement reaction, I just want to go over when we might write no reaction, either in a single replacement or a double replacement. In single replacement, if we have a metal that's by itself, it will replace another metal that's in a compound if the metal in the compound is lower in this activity series that we have over here. Okay, so for example, if you had K and you were adding that to NaCl, potassium is above sodium, so the reaction would happen. The K would replace the Na, so now it's KCl, and the Na would be by itself. If it was the other way around, say we had Na trying to replace K, that's not going to happen because sodium, the metal by itself, is lower in the activity series. So that means that there is no reaction. And you can even write no reaction. Same thing is true for halogens. Okay, if the halogen by itself can replace another halogen in a compound, that's lower on the periodic table. So you have the halogen activity series over here, but it's also the same as the periodic table. So if we had F2 trying to replace Cl in this compound, because F is higher than Cl, that reaction would happen. And then, of course, you need to balance it. Okay. The reason I'm writing F2 and Cl2 is because they're diatomic. So if that's a question that you have, that's the answer. Halogens are diatomic. If you had the other way around and you had Cl2 trying to replace fluorine, Cl2, the element by itself, is lower. So that's going to be no reaction. Okay, so those are just for single replacement. There's no other type that you have to worry about there. Double replacement. So you're going to start with a balanced equation. This will start to fall by the wayside as we go throughout the year and you get more familiar with this. But for right now, we're going to start with a balanced equation. At some point, you're going to get so used to these that you're going to be able to just look at them and see what they're supposed to be. Then you're going to look at what species are soluble and write them as their ions, okay? So for something that to be soluble, it needs to be either labeled as AQ or in solution or something like that, okay? And then you write them as their ions. So an ionic compound that is soluble according to our solubility rules dissociates in water. So if you put salt, NaCl, in water, it breaks up into Na plus and Cl minus. That's what we call dissociating. Okay, other compounds that don't do that just dissolve, and we'll talk more about that later. However, if you have solid Na and you don't put it in water, there is no dissociation. Okay, you just have a block of NaCl. So in order to even make these solubility rules apply, you have to make sure there's either a solution or it says aqueous, like AQ. Okay, it's the same thing. Solution is AQ. So if it says S, there's no breaking apart into ions. That's really important. So you can break those up into their ions and then keep all other substances as molecules. So that means anything that's insoluble, or anything that's solid, liquid, gas. Okay? So keep all other substance as molecules. Insoluble, solid, liquid, gas. Once you've done the dissociation, you can cancel out what we call spectator ions, and I'll explain what that means. And then if all of the spectator ions cancel, we write no reaction. So that's where a double replacement would have no reaction, if all of the spectator ions canceled. So before we get to actual practice on some of these, there's going to be something we call phantoms. And these you need to know. So phantoms, and there's a bunch of them, but the most common ones are going to be carbonic acid, so the ones I want you to memorize, H2OCO3, and ammonium hydroxide, NH4OH. So carbonic acid is going to decompose automatically in an H2O and CO2 whenever it's a product of a reaction. Okay, so if you're writing H2CO3 as a product, like if that's the product you're predicting, you break it up automatically into H2O and CO2. So it's a phantom. It doesn't really exist. Okay, it's a figment. So you can just automatically write it as H2O and CO2. Same for NH4OH. It's going to decompose into H2O and NH3. So as soon as you see that, you can write H2O and NH3, because ammonium hydroxide is a phantom. Another kind of category of phantoms are metal carbonates. So anytime you have a metal attached to CO3, it will change into the metal oxide and carbon dioxide. Okay? So this will happen all the time whenever it's heated, unless it's an alkali metal. Alkali carbonates don't decompose when heated, but they will decompose into that CO2 metal oxide with acid. Okay? So the three phantoms you need to remember are carbonic acid, NH4OH, and any metal carbonate. Okay? So keep those three in mind as we're doing them. And so for this last part, if you had copper to carbonate and you were writing that, you would automatically write it as the metal oxide plus CO2. Okay, now when you write the metal oxide, still use your naming rules and crisscross your charges and everything. It's just that since copper 2 and oxygen both have a charge of 2, it worked out here. Okay, so don't think it's always going to work out. All right, let's jump into some examples. So for this first one, this right here is acetic acid. It's a weak acid. So remember, I told you I would tell you that until we get to our acid unit. So a weak acid, if you look back up at our little rules, means you keep it as a molecule. It does not dissociate. Now, NaOH is an ionic compound. Okay, now we have no states of matter here. If you're not given states of matter, you can just assume that ionic compounds are in solution. It's really when it's specified that it's a solid you want to be careful. Okay, so we can assume this is in solution, which means since it's Na, and that's one of our soluble rules that we know, this is going to break up into Na plus, NOH minus. Then we get to water, which is not an ionic compound. Molecular compounds are always just written as their molecules. And then for sodium acetate, we know it's soluble for the same reason the other one was. Sodium is soluble. And then we have acetate, which is one of those polyatomic ions we memorized. So now what you do is you cancel out anything that shows up on both sides. And it has to show up exactly as is. Okay? So here we have Na plus and we have Na plus. So those will cancel out. Nothing else cancels here, okay? We also have OH minus on before the arrow, but after the arrow, we don't have an OH minus. It is in here, okay? So we can't cancel it out. It does factor into the reaction. So once you've canceled all the spectator ions, you can just rewrite the equation without them. So we end up with acetic acid plus OH minus gives us water plus acetate. So sodium, as soon as we put it in water, a compound with it in water, sodium hydroxide, it dissociates, and then it didn't do anything, okay? It just stayed as Na+, so we don't care about it. We can take it out of our equation. It's not going to factor into the chemistry behind it. When you're doing net ionic equations, at the end you want to make sure it's still balanced, okay? And you also want to make sure the charges are balanced. So here, before the arrow, our overall charge is a minus, and then after the arrow, our overall charge is 1 minus. Okay, so we're good. This is our net ionic equation. Okay, so for this one, we have aluminum metal, which is just Al, and it's dropped into a solution of zinc chloride. Zinc is one of those transition metals that only has one charge, so you need to know it's ZnCl2. It's a single replacement reaction, so the first thing I should do is probably make sure it actually happens. So if I go up to my activity series, aluminum is right here and zinc is right here. Since aluminum, the metal by itself, is higher, this reaction will happen. So then aluminum plus zinc. I'm going to balance this. You can either balance it now or at the end. Either one is fine. Some people are going to prefer one over the other. It just depends on when you want to do the work. So if I put a 3 here, 2, 2, 3, that should balance it. Okay, now here, we need to figure out whether zinc chloride is soluble or not. It's not one of the things we have to memorize, okay? It's not sodium, potassium, or NH4, and it's not NO3. But if we go back up to this, which I want you to have reference and have in your notes throughout the year, when you see the words solution or aqueous to describe an ionic compound, you assume that compound is dissolved and dissociated. So that means it's in water. It also means that we're assuming it's soluble. Okay, so it needs to be dissolved and dissociated. So we're going to break that apart. So I'm going to keep obviously Al, and then I'm going to break up zinc chloride. So for zinc chloride, the 3 goes to both of the elements. So we have 3Zn, and remember the charge is 2 plus. And then for Cl, we have 3 times 2. So you do the coefficient times the subscript, just like you would for balancing. So we're going to have 6Cl minus. Okay, on the other side, we have AlCl3. And that's not one of our soluble rules or compounds or something, but that solution part carries over, okay? Because we're saying that they were in water, they're still in water, and so we're going to assume that AlCl3 is still soluble because our problem mentioned the solution. So that's going to give us 2Al3 plus 6Cl minus plus 3Zn. So this is what I meant by you can balance it at the beginning or the end. It doesn't matter. Like if you don't want to carry over these coefficients and everything, then just wait till the end. Okay, I'll do one of those examples that way as well. So here, now you're going to cancel out anything that shows up on both sides. So we have 2Al, and then after the arrow, we have 2Al3 plus. Does not count. They have to be exactly the same. So we have 3Zn2 plus before the arrow, 3Zn after the arrow. So again, does not count. So now we take 6Cl minus with 6Cl minus. I'm just going to write it down here and then erase it. So then we end up with 2Al plus 3Zn2 plus gives us 2Al3 plus 3Zn. Okay? And this is what I meant. If you wanted to wait until now to put the coefficients in, that's fine. Make sure your charges are also balanced. So here we have 2 plus multiplied by that 3 coefficient. That does apply to the charge. So that's 6 plus. And then we have 3 plus multiplied by the 2. So that's 6 plus. So this is our net ionic equation. I'm just going to erase that so I have room. So this one, solid gold is dropped into a solution of silver nitrate. So this is a single replacement again, so we should check our activity series. Gold is the one by itself. So gold is all the way at the bottom. So, I mean, I don't even have to look up the other one, but here's silver. Gold is the one by itself. Gold, that means the one by itself has to be higher, remember. So here, gold, no reaction. Okay, next one, we have aqueous solution. Okay, so they're telling you this is a thing. So cadmium chloride. Cadmium is another one of those transition metals. And potassium phosphate. Whoops. Okay, so we are told the first two, the reactions, are in solution. So I'm going to break those apart. And I'm going to wait until the end to balance this one so you can see how they both work, and then you can figure out what one works best for you. So cadmium chloride is going to be Cd2 plus 2Cl minus. So still, if we're not balancing till the end, you still need to make sure you account for that subscript. Okay, that subscript said we had 2 Cl's. So we just make it a coefficient. And then we're going to do 3K plus, because of that subscript, plus PO43 minus. PO43 minus is a polyatomic, okay? So when we put polyatomic ions into water, they do not dissociate. So even though we're breaking this apart, you always keep the polyatomic together, okay? When we say dissociate, we mean into its ions. So potassium phosphate is going to dissociate, but phosphate itself is not going to break up into P and O. So then here, we know that KCl is going to break up. Okay, so we're going to assume that the cadmium phosphate doesn't break up, because if not, then we would have nothing here. Okay, so we're just going to assume, because we have no other information, that this doesn't break apart. And then we know that K plus Cl minus does break apart. Okay, so if you don't want to balance at the beginning, you would balance now. Okay, you would balance before you start crossing out spectator ions. Because if you don't, it's going to get really messy. Okay, so if you want to wait, you would balance it right now. So to balance it, I'm going to do a 3 here, a 3 here, 2, and then we're going to need, this is going to need to be 6. This is why I think it's easier to do it before. But I think that works. Okay, so now we can cancel out any spectator ions. So for spectator ions, we have 6Cl minus and 6K plus. So our net ionic equation, which I'll just write down here and then erase, is going to be 3D2 plus, 3CD2 plus 2PO4 3 minus, and then that gives you CD3PO4 2, okay? So that's why I think it's a lot easier to balance at the beginning and just make sure I cycle through those coefficients and subscripts, because I don't really have to worry about the charges. They'll balance out at the end. But here, when I was trying to balance, I had to be wary of the charges. So that's just my 2 cents. You can do whatever makes sense for you. Okay. Now here, we have sodium hydroxide, plus potassium chloride. And that's a double replacement, will give us potassium hydroxide plus sodium chloride. So potassium and sodium are our 2 soluble things that we need to know, or 2 of them. So it would break up into Na plus OH minus plus K plus Cl minus. And then on the other side, we still have potassium and sodium. So we would have K plus OH minus Na plus Cl minus. So you can see that all of these are going to cancel. The Na plus cancels, the OH minus cancels, the K, and the Cl. So for this one, you can just write no reaction. So some people might be thinking, but how come you didn't know the one before was no reaction? Why did we assume there was going to be a precipitate there? Okay, and the answer is you're going to assume that AP will do everything to make a reaction happen unless you know for a fact it's not going to. Okay, so here, this last one, we know for a fact it's not going to because we had all these compounds with potassium and sodium. So based on the rules that we have to know, there was no way a reaction could happen there. But the one above it, based on the rules we have to know, this could be a precipitate. So we're going to assume it is. Okay? So that's what you want to assume AP will have a reaction happen unless you know for a fact based on the stuff you have to memorize or the stuff that's given to you in the problem that there's no chance of a reaction, okay? It's your last resort. And so that's your last one here where you have sodium and potassium. There's no chance of a reaction there. Those are the rules we have to know. All right, so to wrap up this, well, no, we're going to do one more thing after this, but to wrap up this topic, here is some practice for net ionic. So, like we talked about in class, you're going to pause the video here, try the practice, and then come back to see what the answers are so that you can check your work. Okay. So this first one is just a straight net ionic equation. Your nitrates and potassiums will cancel. The second one, HBr is a strong acid. So you would have your sodiums would cancel and your H's would cancel. Oh, sorry. I made that mistake when I was doing it too. Your sodiums and your Brs will cancel. You will then make carbonic acid, which we know is a phantom. That's why I put it in dotted parentheses. So it automatically becomes H2O plus CO2. And then here, hydrogen gas over copper oxide gives water plus copper. There's nothing that's going to cancel out there. Okay? So your net ionic equation is going to be the same as your regular equation. All right, so the last thing I want to talk about when we're talking about dissolving and dissociating is electrolytes, and this will come up a bunch throughout the year. You've heard that word before, I'm sure. Electrolytes are compounds that dissolve and dissociate when you put them in water. Okay, so just like we were talking about all of those soluble ionic compounds, those are all electrolytes. Electrolytes mean that they conduct electricity. So you probably remember from your first year class that conducting electricity just means movement of electrons. So if we dissociate into ions, then there are electrons. There are positive and negative ions floating around. So there are electrons floating around, okay? So soluble ionic compounds and acids or bases. Now, strong or weak just means how much is ionized. Okay, so if we say it's a strong acid, that means it's all ionized, and we'll talk more about that in Unit 3. If it's a weak acid, only some of it is. Concentrated or dilute, just how much of the solvent you put, how much of the solute you put into the solvent. Molecular compounds tend to be non-electrolytes. They don't dissociate, so they don't conduct electricity. So what you might see is observe the orientation of the water molecules. So say we put sodium chloride in water. It would dissociate into Na plus and Cl minus. Water, we know, is a polar molecule where the H's are plus and the oxygen is negative, or slightly negative and slightly positive. So that changes how water will line up. Okay, so that's all this is talking about here. For the plus side, the oxygens are going to go towards the ion. For the chlorine, the hydrogens will go towards it because opposites attract. So that's all this is getting at here. And lastly, we're going to rank the following in increasing conductivity in water. So strongest electrolyte will be at the end, weakest electrolyte will be at the beginning. So this is going to be our weakest. Because it's a molecular compound. It's not an ionic compound. Okay? So that will be our weakest. Both of these are ionic compounds. So then it comes down to how many moles of ions are in the water. KBr is going to break up into K plus Br minus. It's going to dissociate into Kr plus Br minus. Okay, so in the water, we have a 1 here and a 1 here. So this is 2 moles of ions. Zinc hydroxide, we're going to assume is soluble for purposes of this problem. It's going to break up into Zn2 plus and 2OH minus. So we have a 1 here and a 2 here. So that means we have 3 moles of ions. So zinc hydroxide is going to be more conductive because it has 3 moles of ions. The more moles of ions, the more electricity it will conduct. So we're going to put KBr in the middle, and then the strongest one is going to be zinc hydroxide. Okay, so that is it for this video. Okay, feel free to go back and review anything you need to review. And when you come to class, we'll get started on some problems.